Hello. Is there a reason why the class of the 28th isn't uploaded on YouTube? Or
Class from the 28th isn't uploaded. I probably just have not uploaded it
okay.
and didn't realize that I didn't do it yet. I'll check on it and get that uploaded soon.
Thank you very much. Appreciate it.
You're welcome. Yeah, come to think of it, I don't think I did upload last Wednesday's classes, either of them. So yeah, I'll get those up there. Any other questions for me today before we start? All right, I have a couple things that I wanted to mention to you. Just thinking about the next couple of weeks, we're reaching the end of the semester. What I plan on doing is spending tonight finishing up our discussion of alkene and alkane organic reactions, and then getting started on alkynes, and a couple involving alkyl halides are going to be thrown in there as well. And we'll finish that discussion on Wednesday. Then on Monday, this coming Monday, we'll have a review day for the final exam. And the final exam is then Wednesday, a week from this Wednesday. And what I wanted to do tonight is talk about the review day and see what we would like to do. A couple of suggestions I'll put out there. One thing we could do, I always like to start with your questions. So we'll begin the day on Monday answering any questions you might have from the whole semester in your time reviewing for the final, whatever you might have come up with. Then we could spend some time watching me solve problems, if you find that to be the most useful thing. So I can put some problems together from various parts of the semester and I can solve them. We can solve them together. Or alternatively, I just saw something like a final review worksheet. Yes, I could give us some problems for you to work on and make myself available during that class period so that you can ask me questions. That's what I usually do when we're in person. I'll just give some problems to work on in class. And then when anybody runs into a problem, they can just come up and ask me. Which of those two options sounds the most useful to you? So one person said that they find me solving them or us solving them together to be the most useful, the most helpful. Okay. Reasonable request. Me solving them works for somebody else as well. Getting the worksheet ahead of time and going over problems people struggle with, that could be useful. The thing that I'll need from you on that though is let me know what you're struggling with. I've tried that before, and we show up on review day and nobody says anything. No, either the people don't admit what they're struggling with, or they're not really willing to talk about it. So yeah, I am willing to do that. I like the opportunity to work on some problems and ask questions while working through it. It sounds like most of what I'm hearing, I struggle with the fact that the exams are graded. Can we fix that? It would be nice, wouldn't it? Wouldn't it be nice not to have the pressure of grades? I agree with that. Some colleges do that, but can't help you there, at least not right now. What I wanted to find out is just what most people what would be the most useful for the class as a whole. Me solving problems or you solving problems during a time when I'm able to answer questions. Somebody said that spectroscopy was their weak point. We could do some practicing there. Mary would rather learn and understand than worry about grades. Here's a piece of advice there. If you learn and understand, then the grades follow. That's what I find. If you put the time in to understand everything, the grades come. Let's see, content browser, spectra problems, compilation of questions most missed on the prior exams. I like that suggestion. I just got a suggestion in the chat saying compilation of questions most missed on the prior exams. I didn't keep good records of what people missed on those exams. I guess I could run back through them. Tell you what, let's do this. I won't make you decide tonight. See if you can come up with some questions over the next couple of days, and let me know whether you think that me coming up with problems and solving them for you or me giving you problems to work on will be most useful. We'll do it that way. The last thing I see in the chat is protonation of an alcohol to make water a good leaving group. That's actually something from Chem 152. So protonating something with a strong acid is a concept from Chem 152. But we brought it into this semester because the reason you protonate something is to make that water a good leaving group. But yes, we can spend a little time with that. We're going to have some time this Wednesday during class. We'll see. If you have questions on Wednesday, I'll go over them. I saw something about hydride shifts. Good. I'm glad I'm getting these, because these let me know what we'd like the most to spend the most time on. I didn't hear anybody say anything about stereochemistry or alkane stereochemistry and rotations. Nobody said anything about mechanisms. So maybe we can spend less time on those things if that would work for us. But let me know, and I'd be happy to do what works best for you. All right, let's get started. What I want to do first today is to finish up the discussion that we started last time. And this is where we ended up at the end of the last class. We were talking about functional group conversions involving alkenes and alkanes right here. We learned that you can do a radical hydrogenation of an alkene to turn it back into an alkane. And we finished up the day saying that alkanes aren't particularly reactive. We can burn them and you end up with CO2 and water, but that's not really useful from an organic chemistry standpoint. Here's one that is. So the next reaction I want to talk about, which is going to be right here, it is letter O. This is a radical alkylation of an alkane. We're going to take an alkane and turn it into an alkyl halide. What that does is put a leaving group on the molecule. If you can get a chloride or a bromide on there, that makes a good leaving group. And then you can do more of the chemistry that we've discussed that involve getting rid of leaving groups, like substitutions and eliminations. So let's talk about radical halogenation and all the different things we can do with it. And I'll start that discussion by talking about radicals. A radical, it's called a free radical, is something that has an unpaired electron. So if I have this, for example, a chlorine atom, and a chlorine atom has some lone pairs, and if it has an unpaired electron in one of its orbitals, that molecule is called a radical or a free radical. And these things are quite reactive. They're unstable. That electron that is unpaired desperately wants to pair up with another electron. And there's a few ways that that can happen. And that's what I want to discuss on this slide. How can these reactive molecules find an electron to pair up with and make something else new? And here's the first part of this discussion: making the radicals. How do you get radicals in the first place? And one good way to do it is to take a molecule like chlorine, elemental chlorine, single covalent bond, 2 electrons being shared between those 2 chlorine atoms. And if you shine ultraviolet light on it of the right wavelength, so the way that this reactant is given in problems, H nu, if you think back to Chem 151, is the equation that gives us the energy of light. And so we're supplying energy to the molecule in the form of light. That's what the H nu represents. And what happens when you shine ultraviolet light on a chlorine molecule is you break that bond homolytically. One of the 2 shared electrons goes to one chlorine, and the other shared electron goes to the other chlorine. And you end up with 2 chlorine radicals. And that's what gets things going in this radical halogenation reaction. And ultraviolet light is a good way to get it happening. This is called an initiation step, because we've taken a molecule that is not a radical and we've made some radicals. This initiates the radical reaction. So now we have a container filled with these chlorine radicals, and they are looking for some electrons to pair up with. And because they're so high energy, they're so unstable, they can get them from lots of places. So let's say that we have some ethane in the container as well. This is a C2H6 molecule, ethane. And I specifically called out one of the carbon-hydrogen covalent bonds because that's the one we're going to be going after. When this chlorine radical sees that bond, that covalent bond, it's unstable enough that it can reach in and grab one of those 2 shared electrons, and this bond breaks homolytically. So one of these 2 electrons that are bonding carbon and hydrogen come over here, pair with this, and the hydrogen atom goes with it. So an H radical moves over, and you make an HCl molecule. It's now a hydrogen and a chlorine sharing those two electrons. And then the other electron, when this bond breaks homolytically, ends up with this carbon. So a quick reminder about arrows. When we draw two-headed arrows, that means two electrons are moving in a mechanism. A one-headed arrow, these little fishhook arrows, that means one electron is moving. So this step makes some ethyl radicals. Now I have another molecule with an unpaired electron and an HCl molecule. So the chlorine radical that was very unstable, it's happy now. It got the electron that it wanted and it picked up a hydrogen along the way. Now it's HCl. It's good the way it is. But now I have an unstable ethyl radical. This is called a propagation step. We started with a radical, we ended up with a different radical, and it propagates the reaction. Now this radical can go on and react with something else. So this was a propagation step. What can this molecule do? Once I have this ethyl radical, one thing it could do is meet up with one of these chlorine molecules that did not dissociate. You hit it with ultraviolet light and it either came back together or it didn't get hit with ultraviolet light and it hasn't dissociated yet. So it could react with a chlorine molecule in the container. And it does the same thing. This unstable, unpaired electron reaches in and grabs one of these sigma electrons from the chlorine-chlorine bond, and the bond breaks homolytically. One electron comes over and pairs with this one, and it takes the chlorine with it. And what we make is an alkyl halide. And that's what we're after. Taking an alkane and making an alkyl halide. This is also a propagation step because the other product of this step, this part over here, is another chlorine radical. So now this chlorine radical can go do something like the reaction that we just saw above it. Now here's another possibility. This is the thing about radical reactions. You can get a mixture of products. If I have an ethyl radical and it encounters another ethyl radical, these two electrons can pair up. So they're both very reactive. They're both looking for an electron to pair with. And if they encounter each other, I can just bring these two together. And we make a carbon-carbon sigma bond between those two carbons. And we get butane. That's another molecule that can be made here. Now this is called a termination step. Why termination? We started with radicals, we ended up with none. So as far as these radicals are concerned, they're done. Now that doesn't mean that another radical can't come along later and grab another electron from this molecule and put it back into one of our propagation steps, but this made no new radicals. Here's another possibility. An ethyl radical can meet up with a chlorine radical. And they come together in pair. And that's another route to our alkyl halide. An ethyl radical can break apart a chlorine molecule or pair with a chloride radical. And that's another termination step. And then the last one I'll mention is the termination step that goes along with this top one. You can take a chlorine molecule apart and make two chlorine radicals. But two chlorine radicals can also come back together and remake a chlorine molecule. So as you can imagine, this is a soup of reactions where lots of things can happen. And you end up with a mixture of different products. And that's radical halogenation. Now, the nice thing about it, if we do it correctly and use the right halogens, we can take advantage of kinetics and probability to skew the product distribution in a direction that we want it to go, to try to make the product that we wish to make. And that's what I want to do on the next slide. If you have a more complex alkane, something more complex than just ethane, for example, radical halogenation can occur at different rates with different types of carbon-hydrogen bonds, whether they be primary, secondary, or tertiary carbons that are bonded to those hydrogens. Those occur at different rates. And we can take advantage of that. So let me talk about kinetics for a second. And first, I would like to look at this simple example that we saw on the last slide, just ethane. I have two types of carbon. They're both primary carbons, and they're both equivalent. And if I were to run the reaction that we saw on the last slide with chlorine as the halogen, so have some ethane in there, put some chlorine gas in, hit it with ultraviolet light, and your radical reaction starts. This is the alkyl halide that I would end up with. So I put a chlorine onto one of these carbons. And I'm going to say that this sets the relative rate for the rest of the reactions we're going to talk about. Let's say that this occurs at a rate of 1. And now let me do this. Let's look at propane. Now I've introduced a different type of carbon here. This has two primary carbons, the ones at either end, but I now have a secondary carbon in the middle. And my chlorine radical can come and grab an electron from one of these two CH bonds and put a chlorine onto that secondary carbon. This happens faster. It has to do with the stability of radicals. And it's a very similar argument as we did with carbocations. More highly substituted radicals are more stable, just like more highly substituted carbocations. So since this intermediate radical is more stable, this reaction happens 3.5 times faster than the primary carbons halogenate. And then if I introduce a tertiary carbon, so here's 2-methyl propane. Now I have 3 primary carbons in this molecule and a tertiary carbon. And if we look at one of those chlorine radicals coming in and adding on that tertiary carbon, I would get this molecule. And chlorination at a tertiary carbon happens 5 times faster than this top one. And this is a good thing. We can use kinetics to our advantage here and start selectively halogenating, regioselectively halogenating specific parts of a molecule. It's not super useful with chlorine because these rates aren't that different. 5 times faster is not a huge difference in rate. But if we do the same thing with bromine, there's a much bigger difference. And I won't get into the details of why the bromine radicals are different than the chlorine radicals, but if I do this same reaction with bromine, and again, I call the primary site being halogenated our baseline, relative rate of 1. Halogenating a secondary carbon rather than a primary carbon with bromine happens 82 times faster. Now, that's a bigger difference. It happens for every one of these that occur, halogenation at a primary carbon, you're going to get 82 halogenations at that secondary carbon with bromine. And then at a tertiary carbon, if we were to do a radical bromination there to make tertiary butyl bromide, that happens 1,640 times faster than the primary site. So it's radical bromination where we can really start taking advantage of this. And that's what makes this useful. And it also makes it nice because we can predict what the product distributions will be when you're figuring out the regioselectivity of these reactions. It's not too difficult to figure out what your product distribution will be. Okay. Does that trend for iodine as well? I don't remember, actually. I don't remember what the kinetics trend for iodine is. I know that bromine is very different than chlorine, but I can't remember the numbers for iodine. But bromine is useful. That's the one we can concentrate on. So here's what I'm talking about. Here's where we can predict regioselectivity trends in these molecules. If we look at the radical chlorination of 2-methylbutane, that's this molecule, 4 carbons in a chain, methyl group attached to carbon 2. We have 3 different types of hydrogen, of carbon and hydrogen in this molecule. We have primary, which I have colored blue. So this is a primary carbon. These are primary carbons, but they're different sites, right? This primary carbon is attached over here to this CH2, and then these 2 chemically equivalent primary carbons are both attached to this CH. So the primaries, the ones that will halogenate at a relative rate of 1, I made those blue. We also have a secondary carbon. It's the pink one, the CH2. That will halogenate 3.5 times faster than either of these primary sites. Then I have a tertiary carbon, the purple one. And that will halogenate 5 times faster than the primary sites. So let's talk about this. Based on kinetics alone, which product would you expect to be the major product in this reaction? So let's put some chlorine radicals in and let it start reacting with this molecule. And here are the possible products. I could put a chlorine onto either of these 2 methyl groups. Doesn't matter which, it's the same molecule. And halogenate one of those primary sites. Or I could put a halogen onto this tertiary site. Or I could put it onto the secondary site, or I could put it on the other methyl site. Which do you think will be our major product? And why? What I'm sure I heard, so here, there we go, I got an answer. 2-chloro-2-methylbutane, which would put the chlorine here onto this tertiary site. And that's a good guess. Why? Because it happens faster. You're going to be making those 5 times faster than the primary sites and a bit faster than the secondary site. And so based on that alone, yes, I would expect that to be the major product. Good answer. But there's something else we need to take into account. And that is the number of hydrogens that can be substituted at each site. Each equivalent hydrogen represents a place that a radical can attack. And even though something might occur 3 times slower, if it can happen in 3 places, the probability increase makes those 2 processes essentially the same. You know, you're doing it 3 times slower, but you're also making them 3 times more because there's 3 times more sites that you can make. So what we have to do is count up the number of hydrogens on each of these sites and take that into account as well as the kinetics. Here's how that works. So for this first molecule, where I'm going to put a chlorine onto one of these 2 carbons, how many hydrogens are there that I could potentially swap for that chlorine? There are 6 of them. 3 on one methyl and 3 on the other. That takes into account the number of sites that can be halogenated. And then if I multiply that by the relative rate of halogenation, so these primary sites are halogenating at a relative rate of 1, 6 times 1 is 6. So this is the information I need for this molecule where I put a halogen onto one of these 2 primary sites. Here's the other choice, the one that we thought would be the highest. Now, if you look at this site, there's only 1 hydrogen that I can swap out for a chlorine on this tertiary carbon. But it happens 5 times faster. So if I multiply these 2 together, 5 times 1, that gives me a 5. And this is going to be the contribution from the second product. Now the pink site, the secondary site, there are 2 hydrogens that can be swapped out for a chlorine on this site. And if we multiply that by the relative rate of chlorination, which is 3.5, multiply these these two things together, that gives me a 7. And then there's one more site, this other primary one down at the other end. So if I put a chlorine there, there are 3 hydrogens on that site that could potentially be swapped out for the chlorine. And they occur at a relative rate of 1. And if I multiply these two together, that gives me 3. So now, having said that, the fact that the probability of halogenating at those sites couples with the kinetics, which product do you think is going to be made in higher yield? I think it's going to be this one. When you take both of these two things into account, that one has the higher probability of being halogenated. And we can take this one step further. We could figure out what the product distribution will be. What I'm going to do next is add all 4 of these numbers together. I'm going to add the 6 plus the 5 plus the 7 plus the 3. And when I do that, I get 21. And then for each molecule we could potentially make, if you take the contribution from that molecule and divide it by the total, that gives you your product distribution on a fractional basis. And when you multiply that by 100, that gives you a percentage. So in this reaction, 29% of our product is going to be this molecule, this first molecule. Again, how did I do it? I take the contribution from that molecule, multiply the number of hydrogens that can be halogenated by its relative rate, and then divide that by the total of all of them and multiply by 100. So 29% will be this molecule. This one, if I take this 5 and divide it by 21 times 100, 24%. So already the one that we first predicted would be the highest produced molecule is not. Then the pink one, take that 7, divide it by the total, 21, multiply by 100, 33%. And that's going to be the highest yield. That's what we're going to make the most of, but not by much, right? 33%, and this is only trailing by a few percent. So we're making quite a bit of each of these. And then the one that comes in the lowest, if we take this 3 and we divide it by 21, multiply that by 100, that's 14%. So this is a reaction where, even though it's a complicated reaction, it's simple enough to calculate our product distribution based on the kinetics data that we have. So is this reaction regioselective? Yes, it's regioselective for halogenating at this secondary carbon. But again, not by much. Where does 21 come from? I added together each of the contributions from each of my 4 paths. So 6 plus 5 plus 7 plus 3 gives me 21. And then if you divide the number that we got from a single path by the sum of all the paths, that's what gives you the product distribution, the regioselectivity. This 21 is this 21. Now, because bromination better distinguishes between those sites in terms of kinetics, that makes radical bromination much more regioselective. But it's regioselective for a different product. So let's do radical bromination of the same molecule that we just looked at. This time I'm going to add some bromine to this and shine some ultraviolet light on it to break it apart into radicals. And we're going to play the same game. So if I brominate one of these two equivalent primary sites, that's 6 hydrogens that can be replaced in these two equivalent methyls. And they brominate at a relative rate of 1. Multiply those two things together, that gives me a 6. Now for the tertiary site, there's only 1 hydrogen that can be replaced. This one, the purple one. But it halogenates 1,640 times faster than the primary sites. So if I multiply these two things together, 1 times 1,640, I get 1,640. So you can see we have a much bigger difference because of the rate differences for halogenation with bromine. At the secondary site, I have 2 hydrogens that can be replaced with a bromine. It happens at a relative rate of 82 times faster than the primary sites. 82 times 2 is 164. And then down here on the end, it's the same as we saw with the previous one. There are 3 hydrogens that can be produced, and they halogenate, brominate at a relative rate of 1. 3 times 1 is 3. So who's going to win this time with bromination? Now the tertiary site is going to win. And it's the kinetics that's making it happen. What will our product distribution be? Add all these numbers together. 6 plus 1640 plus 164 plus 3. That gives us 1,813. And then if I take each individual contribution and divide it by that 1,813 and multiply by 100, that gives you the fraction of each product, the percentage of each product that we're going to make. So for the first one, 6 divided by 1813, 0.33% of our product will be halogenating here. 1640 divided by 1813 is a big number. And when you multiply that number by 100, 90.4. So we're going to get 90% halogenation regioselectively at that tertiary site. The secondary site, 9%. And then the other primary site down at the other end of the molecule, 0.17%. This will be our product distribution. So we've talked about product distributions before, and we talked about what might be the major product and the minor product, but we left it there. I said, I'm not going to ask for numbers. Will it be 80%, 20%, or what? This reaction, we can pick the numbers. Now, if I asked you a question like this, I would have to give you these relative rates. I don't expect you to memorize any relative rates. I would have to tell you that a tertiary halogenates 1640 times faster than a primary, and a secondary halogenates 82 times faster than a primary. But you'd be able to calculate this. So that's what radical halogenation is all about. And again, what's it for? This is our next slide, but let me use it as a writing space. What's it for? This molecule, which is 2-methylpropane, is very unreactive. There is no nucleophilic site on this molecule. There are no double bonds. There are no lone pairs. Nothing nucleophilic about this molecule. It's also not electrophilic. All the bonds here are essentially nonpolar. So there are no partially positive centers on this molecule that could receive a pair of electrons. This is a very unreactive molecule. However, if I were to do a radical halogenation reaction, and let's do a bromination, I know that I'm going to brominate that tertiary site much faster than secondary sites. And this is the molecule that I end up with. What can I do with this one? Tell me a reaction that I can do involving this molecule that we weren't able to do with the alkane. Any thoughts? Yep. E1, E2, SN1. Notice that this is coming in the chat. Notice that SN2 wasn't included, which is correct because it's a tertiary substrate. I just put a leaving group on the molecule. So if I were to do this in a protic solvent, and I were to use a nucleophile like hydroxide or water, I could turn this into tertiary butyl alcohol. If I were to do this in an aprotic solvent, and I used a strong base like hydroxide, so all I did here was change the solvent. This time we're going to switch from a substitution to an elimination reaction. And we could make it even more so if we heat it up. So let's heat it too. Now we're going to end up with an elimination product. Or if we decided to do this in a protic solvent, that says protic. And I don't have to have a strong base this time. I could use any old base. I would get an E2 reaction to get the elimination product. That's what this radical halogenation is useful for. It takes a molecule that you can't do much with it and opens up a ton of possibilities. What could we do next? So if we wanted to take this molecule and do something else with it, let's say we wanted to turn this into this alcohol. So I got this elimination product and I wanted then to turn it into tertiary butyl alcohol. How can I do that? Do we know any reactions that will take this molecule and turn it into that alcohol? We do. We discussed it in the last class. Does anybody remember?
Any thoughts? We learned 3 ways to make alcohols from alkenes. Two of them gave you the Markovnikov product, which would put the OH on this carbon. One of them gave you the anti-Markovnikov product, which puts the OH on this carbon. One way, oxymercuration. React it with mercury 2+ acetate in water, and then follow that up with some basic sodium borohydride. And we would end up with this alcohol. So I could take this alkene and turn it into that alcohol. Or if I wanted to put the OH here instead, I wanted to make it a primary alcohol, I can do hydroboration. I could react it with borane and then follow it up with hydrogen peroxide in the base. This is organic chemistry. Now, finally, the last week of class, we're really starting to get into the meat of organic chemistry. This is called synthesis. Starting with a particular molecule, which was what? It was this molecule. Starting with 2-methylpropane. Come up with a way to make tertiary butyl alcohol. And I just introduced you to a couple different paths. One, you can run an SN2 substitution with hydroxide or water. And did I say SN? Yeah, SN1 in a protic solvent, and you get the molecule directly. Or we could do it via 2 steps. We could do an elimination followed by an oxymercuration. This is what synthesis is all about. And somebody just understandably admitted this is finally starting to kick their butt. And I agree that this is where organic chemistry starts to get very interesting, but it's when it starts to get more difficult as well, because we have a whole bunch of reactions that we're going to be getting, and we are going to need to keep these in our toolbox so that when we need them, we can pull them out and use them. This semester, I'm introducing us to synthesis, kind of showing us how it works and how one might do this. If you're moving on to Chem 236, this is going to be a big part of the semester. We're going to learn a bunch of new reactions. We're going to learn how to take this tertiary alcohol and turn it into another functional group, turn it into a ketone. And I'm seeing that people are getting worried for next semester. Don't worry, but what I'm teaching you this semester is going to help you leaps and bounds next semester. The better we're able to get a grasp on these basic reactions, the easier next semester is going to be. So it's a little bit harsh to throw all this at you, but it's realistic. And I'm going to be trying my best to prepare you for what we're going to be doing in the, or what, I don't know if you'll be taking it with me, but what you'll be doing in your next class. So that was a lot of time spent on radical halogenation because I wanted to introduce that concept of synthesis here. Okay, 2 more reactions that I'd like to show you here. And I've actually used up almost all of our class today. I didn't plan on doing that. 2 more reactions here. Next one. I can take an alkene and I can turn it into a mixture of aldehydes and ketones by reacting it with ozone. O3 is an ozone molecule. And if we follow that up with acidic reduction in zinc, so we're going to put some zinc in there as a catalyst and add some acid, that gives us an aldehyde or a ketone. This is known as an oxidation reaction, and I'd like to show you how it works. So here's our next one. And I'm not going to give you the full mechanism for this one, but I do want to give you a graphic to help you understand how it works. So here's the reaction. And the alkene that I've chosen here has 3 different alkyl groups on it. And I indicated this by making them 3 different colors. So maybe it's a methyl, an ethyl, and a propyl. Those are my 3 different alkyl groups. And watch what happens. If I react this with ozone, and this is going to be done in an organic solvent, a nonpolar aprotic organic solvent. And then I throw in some zinc to catalyze this next step and some strong acid. These are the molecules I end up with. I'm going to end up with a ketone, 1 mole of ketone, and an aldehyde, 1 mole of aldehyde. Essentially what I've done is split this molecule in half into 2 pieces. This is called ozonolysis. That's the name for this reaction, ozonolysis of an alkene. And even though I'm not showing you the mechanism, I did want to show you the easy way to look at this. So here is my alkene that I'm starting with. And for the sake of this discussion, I just put 4 different things on it. I made them 4 different colored balls. Here's what happens to the molecule. Watch what I'm going to do. I'm going to take this thing and just pull it apart into 2 pieces, the left half and the right half. And each of those 2 carbons that were bonded together doubly are oxidized to carbonyls. So each of the 2 doubly bonded carbons here, this one and this one, are now doubly bonded to an oxygen. Whatever was bound to the left-hand carbon up here stays bound to the left-hand carbon down here. So the purple one and the blue one stay with that carbon. And then whatever was bound to the right-hand carbon over here stays with the right-hand carbon in the product. And that's a good way to think about this reaction. So up here, I specifically made one of these things a hydrogen to show that you can make aldehydes via this reaction if there's a hydrogen attached to one of the carbons, and you could make ketones. So this reaction will either produce 2 moles of aldehyde if you have a hydrogen on each of these 2 doubly bonded carbons. It might make 2 moles of ketone if you don't have any hydrogens bonded to in the vinyl positions to those doubly bonded carbons. Or, like I have up here, you might make a mole of ketone and a mole of aldehyde. That's called ozonolysis. And this is a way to take an alkene and turn it into these carbonyl compounds, aldehydes and ketones. Then in Chem 236, about midway through, halfway through the semester, you're going to start learning about the chemistry of aldehydes and the chemistry of ketones. And you'll be able to take these and do a whole lot more with those once you have them made. That's ozonolysis. And then the last reaction is very similar, except we're using a stronger oxidizer. So ozone was the molecule I used to do the oxidation in P, this reaction. This time I'm going to use potassium permanganate, KMnO4. And I'm going to put that in an acidic solution. And this is going to do essentially the same thing that we did in the last reaction, but there's one difference. If you make an aldehyde, that aldehyde will then be oxidized by the potassium permanganate to a carboxylic acid. That's a reaction you're going to learn in detail next semester, but I just wanted to mention it to you now. So let me show you how this one works. It's going to look almost the same as my previous one. Did I not change my reactants? Oh my gosh. Cut and paste gets me again. There, that's what I meant to write there. So this time we're going to take the same molecule and react it with acidic potassium permanganate. And that gives me a mole of ketone and a mole of carboxylic acid. And without showing the mechanism, without pushing arrows around, using arrows to push electrons around, it works essentially the same. Break the molecule into two pieces and make each of those carbons a carbonyl. Whatever was bound to the left-hand side stays on the left-hand side. Whatever was bound to the right stays on the right. Now, if it turns out that you make an aldehyde as a result, so this part of the molecule right here would make an aldehyde, that aldehyde is then further oxidized by the potassium permanganate to a carboxylic acid. So this one gives you a mole of ketone and a mole of carboxylic acid. If both of the first molecules you make end up being aldehydes, then you make 2 moles of carboxylic acid in the end. If both of the molecules you make are ketones, those don't get further oxidized. They stay as ketones. And then in a case like this, where you have a hydrogen on one side but not on the other, you might get a mole of each, ketone and carboxylic acid. So this is a way of making carboxylic acids out of alkenes. And in Chem236, when we're done talking about aldehydes and ketones, we'll talk about the chemistry of carboxylic acids. And you'll learn more things that you can do with this molecule. And those are all of the alkene reactions. I've seen the comments in the chat. I know that this is starting to sound overwhelming. And the reason why I know that it's starting to sound overwhelming is I remember sitting in this class. Why are aldehydes further oxidized? Because potassium permanganate is a stronger oxidizer.
And that's something that I'm not quite prepared to discuss yet. You'll learn those details in Chem 236. Yeah, that makes sense. Good. What was I saying? Oh yeah, I know it kind of seems overwhelming. The reason I know that is I remember sitting in your seat. I remember taking organic chemistry the first time thinking, there is no way that I'm going to pick up on this stuff. This is way, way overwhelming. But you do. And what it takes is practice. That's the only way to get better at this. And so in this last week of Chem 235, I'm starting to introduce you to it, starting to introduce you to these organic reactions, introduce you to how we might take these reactions and pair them up and get a series of reactions that becomes a synthesis. Then in Chem 236, we will practice, practice, practice. And that's the thing that's going to make this tractable. Do I have an old exam that we could take for practice to emotionally prepare? I'll take a look. One of the things is I like to reuse final exam questions a lot because that lets me compare semester to semester. Because if students can do about the same on the same test, the same final, that helps me kind of standardize how things go from semester to semester. So I don't really hand out old final exams, but I will get some practice together for you. That exam would be wonderful practice, I agree, perfect practice. But it might accomplish your goal, but it wouldn't accomplish mine. Are we doing alkynes on Wednesday? Yes, we are. I was hoping to get started on them today, so we'll just get as far as we can into them on Wednesday. Let me just introduce you to alkynes and what we're going to be doing on Wednesday. The good news is the reactions of alkynes are essentially the same as the reactions for alkenes that we just learned about. But a double bond is left behind. This is an alkyne. I have 2 carbons that are sp hybridized. So using valence bond theory, I'm going to take an s orbital and a p orbital, hybridize them to make 2 sp hybrids on each of these carbons. So this is an sp hybrid, this is an sp hybrid. Here's another one, here's another one. And the end-to-end overlap of 2 sp hybrids is what makes the sigma bond, the single bond, the sigma bond in an alkene. Then the other 2 bonds are pi bonds. So if you sp hybridize, that leaves 2 p orbitals on each carbon unhybridized. One of them, which is perpendicular to the sp hybrids, lies in the plane of the screen. So on each carbon, I have an unhybridized p orbital in the plane of the screen. And then the other one, and this gets kind of hard to draw, is perpendicular to the plane of the screen. So this one is coming out at you. This one is pointing back. I'm trying to make this look as 3-dimensional as I can get it.
right? So these are unhybridized p orbitals. One of the pi bonds comes from the side-to-side overlap of these two red p orbitals. Then the other pi bond comes from the side-to-side overlap of the two blue p orbitals. And that's an alkene. Whatever else is in the molecule is sigma bonded through these sp hybrids. So if I just want to put hydrogens on either side, I can just use the sp hybrids to bond with hydrogen atoms. That's what an alkyne is all about. Now, here's what we're going to be doing next time. If I were to do a reaction like we just looked at, if I were to take this molecule which is an alkyne, and do an oxymercuration. So I'm going to react this with mercury 2+ and follow that up with sodium borohydride, which is one of the reactions we learned about last time. The same thing happens. I'm going to break one of the pi bonds. This makes the Markovnikov alcohol. So a hydrogen is going to attach here, and then I'm going to put an OH here. So the same reaction happens. But because this other pi bond is left behind, this thing can then rearrange into a ketone. So what I'm going to show you next time is that the reactions we learned for alkenes work for alkynes, but there's often a twist because that extra double bond is left behind. And that's what we'll talk about on Wednesday. I just saw a message come in asking for the video of last week's class. Somebody asked me about it at the very beginning of class today. I haven't posted it yet. I forgot. So I'll get that posted right after class. I'll get that up there. It's going to take a little while for YouTube to process it, but I'll get it started right after class. And that brings us to 7:01. Which is too close to the end of class to start talking about anything else. So I'll end it there. I hope I didn't completely scare you away from chemistry today, but it's challenging, but it's very interesting. Once you dig into this and get into synthesis, it's very interesting. So I hope I can keep you interested as well as keep you challenged. So that's all I got for you today. If there are no further questions, let's adjourn and we'll finish up our semester on Wednesday. People are saying they're scared. Again, let me reiterate this. I remember that. I remember taking my first organic chemistry class thinking, I don't know if I want to be a chemist. This is crazy. But it works. You do it. And practice is what gets you there. Don't forget to bring questions if you have them or things that you would like more review on. Bring those to me on Wednesday and I'll make sure I include those on the review day, Monday. All right, anything else? Ooh, I saw a comment, terrified and loving it. That's a good comment. It's terrifying, but it's cool.
All right. Have a good night. I'll see you back here on Wednesday. Take care.